Hello everyone, it's a pleasure to welcome you all once again to this course on inferential discrete mathematics. In the past few classes we have had a look at 5 of the units included in this course. On popular demand and regular feedback from your end, we are having this session as a set of revision problems on a few selected topics in the syllabus. We have covered the unit 1 on logic, the unit 2 on relations, the unit 3 on recurrence relations, the unit 4 on groups, and unit 5 on lattices. Today we'll have a look at a few selected topics in the MCQ format. Now you might have known that your assessment is based on MCQ type questions. So we thought we could give you a practice on how to solve problems from these 4 units in terms of MCQs based on what options you'll have for each question, and such that we'll just have a look at one set of topics in the MCQ format. If you can recall, the first unit was on logic. We discussed true or false statements, truth tables, tautology, tautological implications, equivalences, normal forms, theory of inference and predicate calculus. Now we'll have a look at a few topics in the MCQ format. The first question goes as what you see on your screen. A proposition is a statement which is either true or false but not both. Either it is only false, either it is only true, or it is none of the above. You know that any proposition is denoted by a statement P which can either take a true value or a false value, but never both. You cannot be both, not both. So option 1 will be right. Any given statement P will take either a true value or a false value, but it cannot take both. Next one might be a little unfamiliar to you, but we'll discuss it. A sentence which is both true and false simultaneously is not a statement, but it is a paradox. It is not a paradox, it is a tautology, or it cannot be determined. Now a statement can only be a true or a false statement, but if the statement contains within itself an ambiguous meaning which can either be interpreted as a true statement or a false statement, then we call it as a paradox. It has to be a paradoxical statement. Now let's have a look at specific examples on this. Every triangle is an isosceles triangle. That's your statement here. Now we'll try and assign true or false values to this. Now you know that every triangle cannot be isosceles. You also have equilateral triangles, you have right angle triangles, you have scalene triangles, and so on. You will not always have a triangle which is perfectly isosceles. So this statement takes a false value. Now we are moving into the next idea of a connective combining 2 statements. We have one statement which says it is raining and the other statement saying it is cold. Now what can we say about this statement? This is actually a statement, we know that, and it is actually a compound statement, which means it is a combination of 2 different statements using a connective. There is a connective which combines these 2, and therefore it is a compound statement. Similarly, it is raining or it is cold. This time the only difference is you have a different connective here. It's not the and as a connective, it's an or as a connective. Therefore this is also a compound statement. And now we are going into specifics now. If there are 2 statements P and Q, the compound statement P and you have the connective in the symbolized form is called as a conditional, as a conjunction, as a disjunction, or none of the above. You have these 4 options before you. Now you know that a conditional is denoted by an arrow from one statement to the another. That's for a conditional. And a conjunction is denoted by this symbol, and a disjunction is denoted by this symbol. Now it is obvious that the given connected statement, the P and the Q put together in a single compound statement is a conjunction, because we are using the AND as a connective between the two. Okay. Now we have a specific example on this. The truth value of the statement P, which says the city of Ooty is in Tamil Nadu, and Q, which says 3 and 4 give you 8. Now there is a conjunction here, a conjunction of P and Q, where P talks about the location of a city in a particular state and Q talks about a mathematical equation. Now out of this you can obviously see that the statement P is true and the statement Q is false. 3 and 4 do not give you 8, 3 and 4 give you only 7. Now when you do a conjunction between these two, if you can recall the fundamentals behind the truth values of the connectives, you will see that P and Q will take a true value only when both P and Q are true. Here P is Q and P is true and Q is false, therefore the connected statement will take a false value. If you can slightly make changes here, the statement P says the city of Ooty is in the state of Kerala, and 3 and 4 give you 7. Now this time P takes a false value because we just registered the fact that the city is located in the state of Tamil Nadu, and Q states that 3 and 4 actually give you 7, and that statement is actually right. So P is false, but this time Q is true, therefore the conjunction of these two once again will take up a false value. Now once again we will talk about a disjunction here, the compound statement PQ, where the two individual statements P and Q are connected using a connective of this kind. Now we just saw a few slides back that a conjunction is denoted by this symbol, a conditional is denoted by this symbol, and a disjunction is actually denoted by this symbol. So when you have P and Q in a compound statement using a connective which is of this form, what you have is a disjunction of P and Q. Now we have the exercise to convert the given English sentences into symbolic form. Statement 1 says 5 is a positive integer, and statement 2 says that a square is a rectangle. Now we have a given statement which says 5 is a positive integer or a square is a rectangle. We have these two statements P and Q connected using a connective of this form. The connective here is OR, which is clearly a disjunction. We obviously know that 5 is a positive integer, and we also know that every square is also a rectangle. But we are required to find only the symbolic form of this statement, the quoted statement here. We are required to focus only on the symbolic form. So option B talks about a conditional, option C talks about a conditional, option D talks about a biconditional, none of which is what is being represented here. It is only option A which is right. Option A is about a disjunction because the word OR stands for either one of them may be true. That's what we know. Therefore it is a disjunction, and hence option A is the correct answer. Next up we have the truth value of the statement. Once again we have P and Q. P talks about the location of the city Chennai in the country India, and Q talks about the nature of this number, the square root of 2. Now they have been combined using a connective which is the OR, so it is a disjunction here. We are talking about a disjunction between P and Q. So it's either P or Q which is being which may be true. That's what we are trying to examine. So assigning truth values, we see that P takes a truth value as T and Q takes a truth value as false, because you might very well know that the square root of 2 can best be approximated to the form 1.414, which is clearly not an integer. It's a decimal number, and therefore we will see that the statement Q takes up a false value and the statement P takes up a true value. Therefore the connective P or Q will take up a true value. The last part, now we are asked to have a look at a definition and find out what the definition actually points at. A statement which is generally performed by the introduction of the word not at some proper place in the statement, or by prefixing the statement with it is not the case that, or it is false that. Now all of these three talk about the construction of a statement from a given sentence. 1, you introduce the word not. 2, you had a prefix saying that it is not the case, it is not the case. And 3, you talk about it is false. All of these are specific ways of constructing a new statement. Now can it be a conditional? No, because you know that any conditional is characterized by this phrase, if something then something. That is how you understand a conditional. That's not what you have here. And a conjunction talks about some statement and some other statement. So it is not a conjunction again. And statement 3, some statement or some other statement. None of these match the given description, but this definition called the negation of a statement perfectly defines what we have. The negation of a statement is actually obtained by one of these three methods. Either you introduce the word not in an appropriate place, or you add the prefix stating that it is not the case that something is happening, or you do the thing that it is false, you assign the false value. So it is this option which is best suiting the given definition. Now let's focus on an example, the negation of the statement all men are wise. We are supposed to negate this. So what do you have? First one says not all men are wise. Second one says it is not the case that all men are wise. Third one says it is false that all the men are wise. Now as we saw in the previous slide, each of these three methods can be used to define the negated version of a statement, and that is what is done. Option A negates the given sentence, option B also negates the given sentence, option C also negates the given sentence. Therefore all three options are right. So all the above talks about the negated version of the given sentence. Next up we will discuss the idea of a truth table. Now when P and Q are combined using the conjunction and you try and draw the truth table, how many rows will this truth table have? Now we have solved a lot of problems based on the truth table of a compound statement, and it is obvious that the answer is 4, because I told you before, when the number of statements used to define a compound statement is n, then the corresponding truth table will have 2 power n rows. Now we have seen examples where we have combined 3 different statements and we have had a truth table having 8 rows. We have not discussed the 4 statement case, but even if we discuss the 4 statement case, you will have a truth table containing 16 rows. So the pattern that you can observe here is, when there are n statements considered for the construction of a formula or a compound statement, then the truth table, the corresponding truth table will have 2 power n rows. So we have only 2 statements P and Q here, so the corresponding table will have 2 raised to the power of 2, which is only 4 rows. It can't be 3, it can't be 5, it can't be 6, it has to be 4. And we'll also discuss a few questions on the equivalence nature of these disjunctions and conjunctions. Now what you have here is the negation of the disjunction between P and Q. There is a statement P, there is a statement Q. You have a disjunction between P and Q. You call it as P or Q, and you're trying to negate it. Now, what will it be equivalent to? We've already seen more than one ways of finding the answer. Let's have a look at what the answers are. Option D talks about the conjunction. Option C talks about another conjunction in which one of the statements is negated. Option B talks about the other version of option C, and option A talks about the negation of both, but they are in a conjunction. And there are two ways to understand which of these options will be right. One is by using De Morgan's law. We have already learned what a De Morgan's law is. The negation of a disjunction is the conjunction of their individual negations. So obviously option A is right. And whenever you are faced with such a question and you are uncertain as to which of these options is right, there is also another method to find it out. There is also another method to verify if your actual guess is correct. If you can recall, we did this using the truth table method. So we have P, we have Q, we have their disjunction, and we have its negation. So true, false, true, true, false, true, false, false, and their disjunction is true, 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 and false. When you have a disjunction, you'll have a false value only when both are false. That happens only in the fourth row. Now you're going to flip everything here. So true becomes false, false is false, true is false again, false is true. So that is the set of sequences of outputs that you will get for the given statement. Now you are trying to find out what it is equivalent to, and you have an instinct which says that option 1 may be right due to De Morgan's law. You can always verify this. Let's do these two, because what option A says is you do a conjunction between their negated versions. So negation of P is false, false, true, and true. Negation of Q is true, false, false, and true. And now you are trying to form the conjunction of these two. So when you go for the conjunction, you will know that a true value is returned only when both are true. So that happens only in the last row. All the others are false. So now you will see that column number 4 and column number 7 are exactly the same, and therefore the corresponding statements are equivalent. So option A is right, and this is one another way to find out if your guess, whatever your guess is right or wrong. You can either use De Morgan's law and establish this, or you can draw the truth table for each of the 4 options and verify. I'll leave it as an exercise. You can try options B, C, and D also. You will see that none of them match with column 4 of this truth table. Now the next thing that we saw is classifying a compound statement as being a tautology or a contradiction. We have a statement here, a formula, which talks about a compound statement involving P and Q. There are only 2 statements, so it is easier to draw this. We are asked to classify this as being a tautology or a contradiction. Now if you can remember the definition, you will see that the only way to find out if a given statement is a tautology or a contradiction is by drawing its corresponding truth table. You will have no trouble in recalling that a tautology is a compound statement which has all true values in its output sequence, and a contradiction is a compound statement which has all false values in its last column of the truth table. So let's find out, and that's the only way. You cannot, or you can simplify the given statement, but let's try this. True, false, true, false, true, true, false, false. These are the 4 input sequences you have. Let's flip Q, let's flip P, and then let's do their disjunction. The disjunction is false only in the first row, all other rows are true. And now we'll have to perform the disjunction between columns 1 and column 5 in fact. Now true or false will give you true, false or true is true again, true or true is true, false or true is true again. You will see that all 4 answers for the 4 different input sequences have been true, and therefore what you have here is a tautology. Next is a similar exercise. Once again you are asked to classify whether this compound statement is either a tautology or a contradiction. So you have one for P, one for Q, one for their negation, one for one conjunction between Q and negated P, and that is being involved in a conjunction again. So that's what you have. Now let's try and draw the truth table and see for ourselves whether this compound statement is a tautology or a contradiction. You must have got pretty familiar with what is happening here now, but let's discuss this anyway. We'll flip Q. Let's do the conjunction between columns 1 and 3 true, all the others are false. And let's now do a conjunction between columns 2 and columns 4. False and true is false, true and false is false, true and false is false, false and false is false again. So you will see that all rows in the final column have the truth value as being false, and therefore what you have is a contradiction. Let's have one more example here. So you have P, you have Q, you have negated P, you have negated Q, one disjunction between negated P and Q, one conjunction between P and negated Q. Let's call this A, let's call this B, and you have a disjunction between A and B. Let's classify this again. This is false. We're just going to flip P. This is true. Now let's do a disjunction between columns 2 and 3. False. The first one is false. True again, true again, true again. And a conjunction between columns 1 and 4. True and true is true. False everywhere else. Now a disjunction between these two. False or true is true. True or false is true. True again and true again. You will see that all 4 rows of the truth table have a final truth value as being true. So this is yet again a compound statement that is a tautology. Now that will be the set of questions that we did under logic to have a small revision of the concepts in the MCQ format. Let's go to the second unit on functions and relations. We have discussed this at length during our set of video lectures on this unit exclusively. Now as we did in the previous one, we'll have a look at a few problems on this unit and we'll discuss them in the objective question type. Let n be any two non-empty sets. A relation from A to B is a subset of what Cartesian product? Now if you can recall, the very term of a relation is defined based on this idea of a Cartesian product. Now when you have no Cartesian product, you don't have a relation defined, because a Cartesian product is what you call as a set of all possible ordered pairs involving the two given sets. Now the question talks about the relation which is defined as the subset of a Cartesian product. That Cartesian product, since the relation goes from A to B, can only be this Cartesian product A cross B. These two are not Cartesian products, so they are wrong. The last one is a Cartesian product of the form B cross A, which means you define a relation from set B to set A, and that's not right. So that's not what we want. Therefore options B, C and D are incorrect. Option A suits best the given condition. Now how do you reckon this idea of a Cartesian product? When you have one set 1 2 and one set A B, now what will this set called the Cartesian product have? It will have all ordered pairs, but the first element will always be from set A and the second component of the ordered pair will be from set B. So if you look at this case, option B is not right because option B does not have this pair 2 comma B. Recall that the Cartesian product should contain within itself all possible ordered pairs. So 2 comma B is absent and therefore that's not the Cartesian product. Option C talks about a pair called 2 2. Now 2 2 doesn't make sense because 2 2 is a pair in which both components are from the same set. The first component must be from set A, the second one must be from set B, but here both are from set A and therefore this is also incorrect. The last one, these two and this, they are fine, but the first one talks about AA, where you take an element from the second set and you construct a pair. That's not, and both elements are from the second set. The same mistake that happened in option C, and therefore option D is also incorrect. But the first option, where you see 1 comes from A comes from B, 1 comes from A, B comes from B, 2 comes from A comes from B, 2 comes from A, B comes from B. So option A explains best the Cartesian product A cross B, and therefore option A is the right one. And this is a fundamental question, an elementary question of a function. You have a set 1 2 3, you have a set 3 5 7 8, and you're trying to find out what f of 1 is. Now f of 1 you don't have to worry about, you just have to find the number to which 1 is mapped to. So f of 1 will just be 2 times of 1 plus 1, that's going to be 3. 3 is our option. 4 and 6 cannot be 2, 4 and 6 cannot be because they are not part of the set B and therefore they can't be right. Option C is the only option which makes sense. Now let's what happens here? Now you have the same function between set A containing 1 2 3 and set B containing 3 5 7 8. Then what is the range of f? If you can recall, you will be able to find out that range is the set of all images. Now what is the image of 1? F of 1 is 2 times 1 plus 1, that's 3. F of 2 is 2 times 2 plus 1, that's 5. And f of 3 is 2 times 3 plus 1, that's 7. So the range is actually this set f of 1, f of 2 and f of 3 put together, and we are asked to comment on this set. The range of f is equal to the domain. It's actually not equal to the domain because it misses the element 5 7 8. 8 is missing, so equal 2 cannot come, equal is wrong. Not equal is actually right, because two sets can be equal only when one is a subset of the other in both ways, and you can't have that. They are not equal again. They are not equal, and therefore option B makes sense. Option C talks about a proper subset. Now you will see that 3 5 7 is a proper subset because the set 3 5 7 misses exactly one element, and therefore it is a proper subset. So option B and option C both qualify as the right answer. Once again, this is pretty simple. F of 2 is f of 2 will be 2 times 2 plus 1, that's 5, and option D is right. Okay. Now a father D has 3 sons A, B and C. Now assuming the sons in the set A and the father in the set B, father being the only element in set B, then the relation is a father of from the set B to the set A is, we have 4 options before us. So we have a relation defined from B to A. Now B contains only D, A contains A, B and C. Now what ordered pairs will we have? We'll have D comma A, because D talks about is a father of A. Now that's true. We'll have D comma B and we'll have D comma C. We have a relation, that's easy. We have just written the Cartesian product and all of it are part of the Cartesian product. Now we have 4 options before us. Can you call this relation as a function? or do you know whether it is not a function, or is there some uncertainty whether it may be a function or may not be, or is it none of these? Now it's easily observable that you cannot have three ordered pairs in a function, all of them starting from the element A, because if you can recall, the definition of the function says that every element should have a unique image, should have an image but only one image. You can't map it to three elements like what you have here in this example. So this clearly is not a function. So option A is wrong. Option C, there is no uncertainty. You can very well say that it is not a function. You don't have any uncertainty there, so the uncertainty is also not going to bother us. And option 4 talks about, it just says none of these. None of these is also not right, because you clearly have option B to be correct. Okay, now we'll just define this in another way. Father D has three sons A, B and C. By assuming the sons as a set A and the father as a singleton set B, then the relation is a son of. Now this time the relation moves forward from A to B. So you'll have the ordered pairs like this. It will be A comma D, B comma D and C comma D, because everywhere it says A is a son of D, B is a son of D and C is a son of D. So that makes sense. That makes sense. So these three ordered pairs are what you will find in this relation. Now can you call this a function again? This time yes, you can call it as a function, because every element in set A has three elements, have an image, every element has an image, no element has two images and no element is left out. So every element has an image, every element has only one image, and therefore it is clearly a function. And you can't find any evidence to support option B. Option B is not right, and there is no uncertainty also. You are very clear, it is very obvious that this relation actually forms a function, and none of the above is also not applicable here. Alright, now let's talk about one more function from one set of real numbers to itself. We'll have a function defined from real numbers to real numbers. Then the range of f, talking about the range of f. Now if you can recall, the set of real numbers includes every positive integer, negative integer, zero, rational numbers, irrational numbers, decimal numbers, all of them are under the same roof. Now we are defining a function where an element is taken as an input and squared. So you will have 1 mapped to 1, 2 mapped to 4, 3 mapped to 9, minus 1 mapped to 1 again, minus 2 mapped to 4 again, minus 3 mapped to 9 again, so on and so forth. Now we are worried about, no, the question in fact wants you to discuss the range of the function. Now let's look at the options. Option 1 says the range is the set of all real numbers without 0, which means I am excluding 0 and I am saying every other real number is a part of the range. Option B similarly says every real number except 1 is included. Option C says every real number except 2 is included. Option D says none of them is right. If you can watch, you will obviously see that none of these options is in fact correct, because option 1 is wrong, because 0 is clearly part of the range, because 0 squared is 0, so you will have an ordered pair 0 0, and we clearly saw that both 1 1 and minus 1 are part, so 1 is also an image. You can recall that range is a set of all images. So option 1 is wrong, option 2 is wrong. Option 3 talks about every real number other than 2. That's not right. That's not right, because in fact you don't have the real number as minus 2, which is an image of any number. You can't square any real number and get minus 2. Option C says exactly that. Option C wants us to delete the element 2 and consider every other element, and says that that this modified set forms the range, and that's not right. In fact, it is none of the above. Now the range of this function is actually all numbers which are non-negative. Every number in this interval is actually the range of the given function, because 0 is the square of 0, and the square of any real number can never be negative. So all non-negative real numbers are part of this range. Negative numbers are not part of this range, and therefore options A, option B, option C are incorrect. It's only option D which is right, because option D says none of these is right, and that suits best the actual range. And now we have a different relation. Let n denote the set of all natural numbers greater than or equal to 2. We have natural numbers greater than 2 and up north, and we say any two natural numbers m and n are related if their GCD is greater than 1. Now we had a look at this GCD when we discussed this thing called as a lattice. I'll recall that particular concept again. The GCD of 2 and 4 is in fact 2, because the greatest common divisor, 1 divides 2, 1 divides 4, 2 divides 2 and 2 divides 4. No other number divides both 2 and 4. So only 1 and 2 are the common divisors, out of which 2 is the greatest. So here it says two numbers m and n are related. They are related if their GCD, the GCD of m and n, is actually greater than 1. Now let's try and find whether this relation is either reflexive or symmetric or transitive or one of them. Can this be reflexive? What is the GCD of 2 and 2? The only numbers that divide 2 and 2 again are 1 and 2 again, and the greatest common divisor is 2 again. So GCD of 2 and 2, when you compare 2 and 2, GCD is 2 again, so that's okay. The GCD is going to be greater than 1. 3 and 3 is 3, 19 and 19 is 19, 27 and 27 is 21. So 27 is, therefore this relation is in fact reflexive. Can we call it symmetric? Now we saw that the GCD of 2 and 4, the GCD of 2 and 4 is 2. Therefore 2 is related to 4. Now, does it mean we can say 4 is also related to 2? Yes, in fact, because when you take two numbers for GCD, the order doesn't actually matter. You're just comparing two numbers and finding the GCD. So the GCD of 2 and 15 is the same as the GCD of 15 and 2. So the order in which you group these numbers is not going to play a part. Therefore it is in fact symmetric. Is it also transitive? Now you know that GCD of 2 and 4 is 2, and the GCD of 4 and 8 is 4. Both of them are greater than 1. Now what if we compare 2 and 8? 2 and 8 GCD is again 2. So these two have been paired up, and these two have been paired up, which means 2 and 8 can also be paired up. So this relation is all of reflexive, symmetric, and all this option C is right. It's all of reflexive, symmetric, and transitive. Okay, now what happens if we count the number of elements in the Cartesian product? A set P has P elements, the set has P elements, the set A has P elements, and the set B has Q elements. The number of elements in the Cartesian product of A and B is either P square, P plus Q plus 1, and PQ. Now we have already seen that when you list all ordered pairs, you will have Q choices for the first element in P, Q choices for the second element in P, and Q choices for all the P elements in P. Therefore the option is PQ. It's not P square, it's not P plus Q, not P plus Q plus 1, it is PQ. Okay, now let's go to classifying functions. The range of a function is equal to the codomain of the function. Then how do you call this function as? Now we have seen this before. We have seen this in this example a little while back when we discussed the range of the function and the codomain. Here the range is not equal to the codomain. The codomain is the set of all real numbers, and not all of them are included in the range. Only the non-negative numbers are included, and therefore this is an example of a function whose range and codomain are different. Now what if you have the same set to be both the range and the codomain? That's exactly what you call as an onto function. An onto function or a surjective function is one function where the range and the codomain are one and the same. They're not different. Therefore onto function is what is right here. Okay, next up we have the same function f of x is x squared, and we're trying to classify f as a one-to-one function or an onto function or both one-to-one or none of them. So it's easy, you can recall once again how this set is being formed. We have negative real numbers. I'm just including the integers. You can also consider all such numbers. You're starting to map them. Minus 3 goes to 9. I'll use a different pen for that. Minus 3 goes to 9, 3 also goes to 9. 2 goes to 4, minus 2 also goes to 4. Minus 1 goes to 1, 1 also goes to 1, 0 goes to 0. That's how this function is actually defined. Now can you call this function as one-to-one? Now you can actually not call this function as one-to-one, because both minus 3 and plus 3 are mapped to the same number 9. So it's actually a many-to-one function, not one-to-one, therefore this is wrong. And we just now saw that this function cannot be an onto function because 7 doesn't have, or minus 3 doesn't have a pre-image in the set of real numbers. You take any real number, the square is always going to be positive, it cannot be negative. Therefore minus 3 cannot be the square of any real number, and therefore minus 3 doesn't have a pre-image, therefore it is not onto. And it is not one-to-one, it is not onto, it can't be both, therefore it is in fact none of the above. So the one description that you can give for this function is you can call this function as a many-to-one function, which is also into. Any function that is into has at least one number that is not mapped to a element in the domain. Here you see that minus 3 is not mapped to any number, minus 2 is not mapped to any number, no negative is mapped to any number here, therefore it is many-to-one as well as into. That doesn't fit any of these conditions given here, so that's okay. Now we have a different definition. F from R to R, again real numbers to real numbers, but this time the function is a lot simpler. F of x is just x. So minus 1 is mapped to minus 1, 0 is mapped to 0, 3 is mapped to 3, so on and so forth. Every number is getting mapped to itself. Now can that function be one-to-one? It has to be one-to-one, because you can't map minus 2 and plus 2 to the same number called plus 2, because they are not same. That's not possible. Only 2 gets mapped to 2. So only one number gets mapped to a particular number, so it's definitely one-to-one. Is it not onto? In fact it is onto, because every number in the codomain will have itself as its pre-image, so it is in fact onto, therefore option B is incorrect. And option C talks about both one-to-one and onto, it is right also, because it is actually one-to-one and also onto, both conditions are being met, therefore it is both of them. None of these is obviously incorrect. Okay, the range of the function is equal to the codomain of the function is called as a onto function. We have already seen this. That's not what you call as a one-to-one, that's not what you call as both, that's what you call as none of the above. It is actually an onto function. Okay, now you have a specific example for a function from set x to set y, where a is mapped to c, b is mapped to d, and the function is defined in the form of a collection of ordered pairs. You call it as ac, bd, both included in the function. Can you call this function as a one-to-one function? Yes, it is one-to-one, both because the images of a and b are different. A and b are getting mapped to different numbers. There is no repetition, no two elements getting mapped to the same element, therefore it is one-to-one. Is it onto? It's not onto again, because E doesn't have any pre-image. And is it surjective? Because both these are one and the same. Surjective is the other name that you give to an onto function. That's also incorrect. None of these also doesn't match the requirements, because it is in fact an onto function. A function f has an inverse function defined if and only if we have a couple of options. If you can recall, we discussed this when we were discussing inverse of functions, and any function will have an inverse only if it is bijective, which means it is both one-to-one and onto. In all other cases you cannot define the inverse function, and therefore this is the only case which fits. If it's only one-to-one, you rule it out. If it's only onto, you also rule it out, and option A fits the requirement, so option D is also not the best answer. Now let's have one more example where A goes to D and B goes to D, and you will see that f is actually not a one-to-one function, because both A and B get mapped to the same element D. You have A to D, you also have B to D, so you have more than one number going to the same number, so it's not one-to-one. It is also not onto, because you have C and D which are left out. There are no images for C, no images for D, for E, therefore onto is also not proper, and it is not injective, because injection talks about a one-to-one function again. If option A is wrong, option C is also wrong. None of these is what suits the bill. It is actually a many to one into function, just like the x squared function we saw.